Well, I can send you the picture of the one
Recording is on. Recording is on.
Recording is on. Recording is on. Recording is on. Okay.
Good evening, gentlemen.
Good evening. Let me take your hot. Okay, we'll just wait a few minutes here. See if anybody else is going to join. We're at, what, 10 so far? Yeah.
I'm trying to think who's missing. Well, I can think of a couple.
As I mentioned to Peter today, I'm going to be a little bit scarce here, and I don't even have my camera on because whatever, long story.
Bedhead.
I'm departing for New Jersey tomorrow morning, and down the home stretch now. So, actually, no, I'll save this for later. Oh, stop.
Come on,
I
don't
have a show and tell here, so. But I'm going to be a little scarce because I have to help, because my better half leaves for Australia for 3 weeks tomorrow as well, and she's got a new phone, and I have a new phone too, actually, but a new anyway, whatever. Long stories, too many stories, too many things going on,
Stories.
and then I have like people asking me if hotel things are confirmed and all that, like retired people asking me if, like, I just don't have time. Not enough cycles.
We don't have time for long stories.
You tell them, Pete.
Yeah.
I'll be
Eric,
back.
just
Yep.
make sure you come back. Don't
Yes.
be late. Don't be late for the after meeting.
Well, I've got one full day in Atlantic City, so I might not come back if I hit it big, right?
I'm talking about after the homebrew meeting.
That. Oh, I thought you meant after my trip. Okay.
No.
Yeah.
Or the Goodfellas get them.
What state did The Sopranos take place in? Wasn't it New Jersey?
Or the Jersey Housewives.
Well, that'll get you going with the Sopranos.
Jersey, real Jersey housewives. I'll be back in a sec, guys.
Yeah, I guess that's wrong state. Where's Atlantic City? What state's that in?
It's New Jersey. It's just about an hour south of where the Vintage Computer Festival is going to be.
Yeah, okay.
Is there much there anymore? I thought like all the Trump stuff closed because it went bankrupt, right? But is there really that many casinos there anymore?
I think they're all
I think so.
down. They've been run down for several years, so.
Oh, I think they're still going. I'll let you know. I just was playing a hand of cribbage with a friend or two about an hour ago, and yeah, I know. I was delivering farm eggs, and he said, "You want to come in for a beer, and then you want to play some cribbage?" Okay, well, I shouldn't really because I'm going to be late and disorganized for my ham meeting, but whatever. It sounded tempting, so I did the deed, and I lost, unfortunately, but whatever. How did I start this conversation? Anyway, whatever.
How many eggs did you win?
I can kick you out to end it if you want.
It wasn't for money, but I said, "Hey, do you want me to put some money down for you?" He says, "I got $10 US. Sure, do it. Put it on the slots. I might just put it on the craps table. Better odds." But
you know what the biggest bang for your buck is? Roulette.
Craps.
Roulette. It takes you. Any game you play there, you're going to lose your money. It just takes you a lot longer to lose your money at roulette.
I don't know. Put it all on the 00.
It sounds like we should maybe play some poker at
Here we go. Nickel poker with you. That's all.
Hey, Eric, if you're going to Atlantic City and it's run down, you better have one of these.
Oh, nice. Well, you know what? You're on the way, so I'll stop in. I can't find my buck knife. It's been misplaced.
I have to go find mine, digging through my camping stuff.
All right, I'll be back in 1 sec, even though you don't know I've left.
No,
You just told us.
Who did we lose?
Okay, we'll wait for.
Oh, we lost Michael.
Hey, Pete.
Yeah.
I didn't know you changed your name to Felogister.
Tyler.
Okay, who's here? Dwayne, Eric, fellow Gister, Frank, Kevin, Hassan, Howard, and Michael.
How come I can't see my own picture? Can you see? You guys see my picture?
No,
No. Okay.
camera off.
I don't think so. The little icon at the bottom says it's on. Okay.
What do you have your performance settings at?
Where do I even look for that?
On the toolbar far right, there's 3 dots.
Yeah. Okay. Performance settings. Highest quality.
Does your camera have a shield?
No.
It doesn't have a physical shield or a button to turn it on?
No, I got to go check the camera in the computer settings. Anyway, carry on. I can hear you. It's okay.
Or turn down to a lower setting.
Oh, okay. The performance, you mean? Okay,
Yeah.
This is
Don't set it to the lowest one because it turns the camera off.
this is sort of the middle one.
Unplug and replug. Cold start.
Yeah. Yeah, you're working fine this afternoon.
No idea. No idea.
Okay.
Don't worry about it. I'll
Let me
figure
try
it out.
this.
All right, let's get started here. Oh, there's Eric.
So this is where I was this afternoon. Not this is where I was, but for those of you that are coming to the cottage, I have a new toy here. I'm just going to show you that. But
Up.
What,
Dave is going to. Oh no, I'm not going to show you any more than that. This is just a teaser. Dave's going to say, just start shaking his head.
what's that? An empty icon box?
It's not empty. Trust me. So
Oh, it looks pretty big.
it's big. I can't show you any more. I can maybe show you this, but I'm not going to show you any more than that.
Oh, I see that.
There
HF.
you go.
It's a
Oh, the IC7300.
400
you
or something.
fucker. Oh my god.
I knew it.
Yes. So,
Does that come with a Canadian call sign?
I don't know. I'm not even authorized to operate it. I don't think so. With my technician license. So. Anyway, I
Reason why you're going up to the cottage.
Reserved.
Is that the door prize?
That's the door.
That's yeah, that's the main poker
Oh, I know why.
gambling.
Yeah,
That's okay.
exactly. That's what I have to now pay for. So,
I got antennas that'll blow it. Don't worry about it.
and it's funny. So I'm sitting there at Radio World this afternoon, and then all of a sudden I hear this voice beside me, and it's like, I know that voice. I look over, and he's in his construction hat, and he's got his overalls on. Mario, what are you doing here? So it's a buddy of mine who actually he's a patient at the pharmacy, but I shouldn't probably be disclosing that. But anyway, whatever. He is also a ham buddy, and he was there picking up some 80-meter dipole. He's creating a phased dipole array. So he was in a few weeks ago and was telling me about his latest acquisition, which is an FT101D DX, not a cheap radio. So I figured, I don't know, I got to at least keep in the game. So.
Okay. All right, let's get started here.
I
Nobody.
figured it out.
Oh, excellent.
Helps to use Google or Chrome.
Okay, let's get started here. So Peter want me to remind everybody who's participating at Eric's to hang around at the end of the meeting. I guess there's going to be some discussion. Unfortunately, I can't go. I can't book that time off. All my vacations been booked already. So yeah, too bad. Would have been nice to get away from the pain in the arse.
So we're just going to be talking about some specifics, but it is just so you can mull over it if you're still on the fence. May 1st to May 8th. Think about it during the meeting this evening. Come up for a day, for a night, for 7 nights. Doesn't matter. So lots of space. Okay, but anyway, we'll talk more about it at the end.
Oh, maybe I'll come one day on the weekend.
Sure.
Was it May 1st to 8th?
1st to 8th, and the 1st is just a park day, right? But it's right through Saturday the 7th all day, and then depart like early on the 8th. So
Okay.
Yeah.
Alrighty. Okay, let's get started here. Welcome everybody to our regular Wednesday meeting. On the agenda tonight is Dave with part 3 of his journey down the rabbit hole. Peter is going to talk about LT spice tips and the Monte Carlo analysis. Wayne's going to share some gadgets, and Kevin's going to talk cool chip. And I got something at the end too I want to discuss. Anyways, you ready to go there, Dave?
Yeah, sure.
Okay, take it away.
Let me just share my screen. There, you guys should be able to see my screen.
Yeah.
So I was in the grocery store today, and I'm walking out the parking lot, and a car pulls in, and the guy's got a VE3 plate. And so me, I'm just chatty. So I go up to the guy, start talking to him, and it's VE3 TDI. He says it's tall, dumb idiot. That's what he calls himself. So we had a great little chat, and he's in the Brantford area. He's a fellow ham, and so it's amazing who you meet when you're just putting around. Okay, so this is the third installment. I think you guys already heard the spiel. It all started with me looking at laser printer, etching boards, and how they use PWM, and they turned out to use a buck converter. And I started playing around with a buck converter, and led me down a whole bunch of rabbit holes trying to figure out why the buck converter wasn't working in LT Spice. And that leads us to today's talk, which is about the transceiver Pete and I were working on back in, I think, 2018 or circa 2018, around that time. We started working on this, and it's more of a log. It's not really anything. I'm just going to talk about what the issues I had. So, in our last episode, last talk, we talked about the buck converter and how I needed a high side bootstrap and how there are chips available to do this and to get the buck converter, and is able finally to get the buck converter to work based on this design here. So everyone was all happy and good. And that before I figured out it was this high side bootstrap was the issue, I got down the rabbit hole looking at MOSFETs, and I learned that there's all these there's all these capacitors or capacitances involved, and they're denoted here in the data sheet. This is for the IRF 510. And I did a simulation where I created a little model of a MOSFET to simulate the input impedance seen here, looking into the MOSFET, and I compared the two, and it comes out almost identical. So I was able to calculate what the capacitances were here, and as you could see, at higher frequencies, the MOSFET basically shorts out because it's got capacitors, and at high frequency, the capacitor represents a short, right? So then I went on to say, okay, well, if the IRF 510 shorts out at higher frequencies, what about some other MOSFETs? So I went through and I looked at some other MOSFETs, and sure enough, they all kind of short out at higher frequencies. And there were a couple where you got fairly higher impedances. Here's, almost 150 ohms at the 10 meter band. At 29 megahertz, you got 100, just over 100 ohms of impedance of of magnitude of impedance. And so this, could be a potential MOSFET to use in a power amp. So that led me to go back to my Dueling 612 transceiver and a power amp and, look at maybe improving that. So in this talk, what I'm going to talk about, just talk a little bit about the 612 and the power amp, and going to talk about the ugly rears its head. Yeah, that's a picture of Eric from high school. And then, I took a look at some popular power amps, and I thought, let me pick those power amps and then maybe start analyzing them and substituting in MOSFETs to see which one would work out the best. So the Dueling 612, I called it the Dueling 612 D612, and it's based on Pete Giuliano's Sudden 40. And here's a design of his Sudden 40. It's got two SA not 602, 612s. They don't make 602s anymore. So they're 612s, and because there are two of them, I said it's dueling 612s, right? And so he built this Sudden 40-meter transceiver, and so we talked about it, and I thought this is a cool design. Maybe there is a way I could make this into a multi-band transceiver. So I gotta bug up my ass, a booma, about these transceivers, because they're all, single frequency, and I understand why. It's tuned components, but it'd be really nice to have a transceiver that's multi-frequency, multi-band. So what I did was I took Pete's design and I came up with some design goals. One of which I changed the 9 megahertz IF here. He used a filter from the GQRP Club. They sell these 9 megahertz filters, and he used that. I decided to use the 12 megahertz IF, and that's why I wrote that program, that little program in Java, which analyzes combinations of IFs and RFs and VFOs and not VFO, oscillators, and look to see whether anything folds back, and you'll get birdies coming back in. So I wrote that program, and 12 megahertz looked promising. And then I found out that if you look at the BitX40, let's see. I'm deleting some files here. Yeah, if you look at the BitX40, it uses a 12 megahertz IF, which was kind of interesting. So, and I also wanted to use pluggable bandpass filter and low pass filters, as opposed to having relay switching between them. It would be so much easier to plug in. Oh, come on! Plug in modules. I was just trying to keep the size as small as possible, and I wanted to use op amps because there's a lot of discrete components, and I felt op amps, there are op amps out there that you can use. And the other thing too is this was a fixed gain transmit power. It was a fixed transmit power, and I wanted to be able to control it. So I wanted to be able to control the gain at the preamp, the RF preamp, and as well control the power output. And also I wanted to use LM386 as opposed to using a discrete amplifier. I wanted to put a S meter, power meter, and SWR meter all integrated in it. And I wanted to use the PARC SIGGEN board that we have, just repurpose the software in it and use that to control the radio. So this is what I ended up on, and this is what Pete and I built. Starts off with, you've got the SIGGEN, which is controlling various things. It's controlling a relay to switch power between transmit and receive. And it's also using that to switch the antenna relays to go from transmit to receive. And it's got a couple of relays here where it's switching inputs and outputs to and from the 612. So if you follow the chain, the receive chain, it comes through the relay, hits two LT1253 op amps that have a gain control, and that way I can adjust the gain. It's got a bandpass filter, and it's got a transformer to match the 50 ohm bandpass filter to the SA612, which I think it's 1300 or 1500 ohms. So the relay switches that to the 612. Then the 612 has the transformer to match it to the impedance of the crystal filter. And same thing the other side. It's got a same thing crystal filter, a transformer to match the 612. So this 612's taking it to the taking the input to the 12 megahertz IF, and this 612 here is now taking it back down to audio. And so the relay switching it to the audio amp, the AF audio amp goes to speaker, and then I've got an S meter circuit, and that goes to the SIGGEN to record the S meter reading. And then on transmit, similar, you've got a push to talk, which is connected to the SIGGEN. So once that push to talk is enabled, the SIGGEN switches the power from receive to transmit and controls these relays. So you've got a mic amp that goes to the 612. The SIGGEN is going to generate a frequency. It's going to take it up to the 12 megahertz IF, and it's going to select the upper or lower sideband and take that out to the 612, the next 612, which is then going to lift that up to whatever band you want it on. And that comes out a transformer, which matches it to the 50 ohms of the bandpass filter. That goes through two LT1253 op amps, again with variable gain, goes to a driver, goes to a power amp, a low pass filter, goes to a SWR bridge that feeds to the SIGGEN to read the power and SWR, and then that goes to the antenna. So that's basically in a nutshell how it works. And this is the schematic of the power amp, because that's what I want to focus in on this talk. So here's the LT Spice of the power amp. It's got the IRF 510, 2219 driver. Then it's got the two op amps, the 1253. Those are linear technology op amps, and they're video op amps, low noise. And I lifted this configuration here from the DDS60 that Midnight Design Solutions uses, except they're using AD 8008 op amps. I chose to use the LT 1253. Number one, because it's a native op amp in LT Spice, and I had a bunch of them kicking around, and they're discrete. They're 8-bit DIP packages. So I chose to use those. So, and if I did a Bode, well, it's pronounced Bodie, but I call it Bode, whatever. If you do a Bode plot of it, you'll see that it rolls off quite substantially. And later on, I'll talk a little bit about these Bode plots, that they could be very, very misleading. But you'll see it's got quite a bit of roll off here. You're dropping from 60, you got about 20 dB of roll off. Now, it just so happens because I can adjust the gain here, I've got pots, I can bring this piece back up, and I can get almost 5 watts out at these higher frequencies. So here's what the board looks like. So here's the RF front end here. There's the RF amp coming in with the two pots to adjust the two op amps. There's the bandpass filter coming in, transformer, the relay that switches it to the SA612. Here's the transformer to the crystal filter, transformer to the other SA612. You can barely see it, it's dark there. Then the relay that switches that to the audio portion of the radio here, and it's got a couple of it's got a one pot here for adjusting the audio gain and another pot for calibrating the S meter. And then on transmit, you've got the mic amp here, right? And you've got adjustable gain, or I could adjust the gain of the mic amp. Goes through the relay, switches to the SA612, same thing, blah, 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 through the crystal filter. Relay switches it to a transformer, goes to another bandpass filter, and here's the output pre-driver, the LT1253 here, 2 op amps, 2 gain controls, the 2219 driver, the IRF 510, low pass filter. Here's the bias, that adjusts the bias for the IRF 510, bandpass filter, and here's the bridge. And those 2 wires are taking the measurements from the bridge to the SIGGEN. And so in a nutshell, that's what it was. And so I was able, here's a contact I made using FT8 as is. Here it is on 80 meters. You can see I'm putting out 4 watts, about 4 watts and change. SWR is 1 to 1.02, which is pretty damn good. And so I was able to make a contact, but I didn't realize, but there was a bug in this. So here it is, making a contact in 40 meters. You can barely see my call sign there. There's a video I made on my channel where you could see this. Here it is on 30 meters. And again, there's a bug in this. And here it is on 20 meters. And here's, 20 meters, I'm putting out 4 watts, SWR of 1.45. And I think I was using my off-center fed dipole. That was before it got ripped down in a storm. So spurious emission rears its ugly head. So now just to give context here, in the US, if you look at what the FCC says, it says the mean power of any spurious emission must be at least 43 dB below the fundamental emission. So it's kind of like DBC. So that's like 43 dBc. DBC is, dB below the carrier, dB relative to the carrier, right? So this is kind of like a DBC measurement, right? So if you look at the ITU says, it should be 80 dBc, right? And in Canada, I had a Dickens finding this. Finally, I stumbled across it. Industry Canada says it has to be 43 dB plus 10 log of the power, or 70 dB, which is less stringent. And that's basically anything outside of 250% of the authorized bandwidth. So this is what, harmonics. It's going to fall. That's what is going to drive harmonics. So, if you look at 5 watts, that's 43.7. And for 10 watts, it's 44. So I said, okay, let's just say 44. Let's go with 44 dBc. So from my main carrier that I'm going to be putting out, all harmonics must be 44 dB below that. So the issue I had, once, I'd made those contacts, I came back, and I think I was at Dayton, and I picked up a publication at Dayton. And do I have no, I didn't put the picture of the publication, but I got a little booklet about FCC regulations, and it was at Dayton, I think in 2019 probably. And I was thumbing through it, and I came across this 43 dB limit. And I thought, oh, well, I wonder what's going on. So I connected the D612 to my SA, and I was surprised to see that, it was in the 30 dB. There was, I think, one band was over 40 dB, and most of the other bands, the harmonics, were in the 30s, like 38, 35, 38, 39 dB, which meant it wasn't legal. This radio, could not be put on the air. And I had to adjust I'd put quite a bit of gain on that pre-driver, the LT 1253 op amps, to get 4 or 5 watts output. And when I adjusted the gain there, the harmonics got even worse. So with the same gain, I'm not touching the op amps at all. At 5 watts, I was getting 5 watts at 7 megahertz, and I'd get 1.7 watts at 14 megahertz. So there was quite a bit of roll off here, and that should come as no surprise based on my previous presentations where you saw that these MOSFETs basically are acting like a short at higher frequencies. So bottom line, the power amp was too dirty, and that made a lot of sense, because even making those contacts, it was very difficult. I had to keep trying and trying and trying. So finally, I threw that radio against the wall and I abandoned it, and I never looked at it until recently. I started to relook at that. So after looking at MOSFETs and the capacitance involved in them, I thought, okay, well, you know what? Maybe I should revisit my D612 and I should dust it off and find a better power amp. So I went searching around, and I looked at all kinds of designs, and basically they're the same. They're all the same. There's a few little subtle differences, but all these amps are the same. It's either a single IRF 510 or it's a push-pull configuration. And so I thought, okay, let me focus on the BitX and Hans Summers, because Hans Summers, he's got quite a bit of success. He's got a 10-watt power amp kit, and looks very, very promising and puts out some good power. So I thought, let me focus on these power amps. So if you I'm not going to go through the schematics. I'm just showing you that this was the original BitX 20 power amp. It had a 2219 driver, IRF 510, similar to what I'm using in mine. And if you do the Bodie plot, this is what you would get. You would get, a roll off of 15 dB between, 1.9 megahertz to 29 megahertz. But I couldn't understand, as I figured out how to do measurements in LT Spice, I could do measurements of frequency of gain doing transient analysis as opposed to doing AC analysis. And I learned something about AC analysis versus transient analysis. When you use AC analysis, it assumes a small signal model. And number two, it assumes a linear behavior. So if your MOSFET has any nonlinear behavior, or any components have a nonlinear behavior, the Bodie plot does not account for it in LT Spice. So that's why I saw quite a bit of difference here between, if you look at 29 megahertz, I was seeing 30 dB of gain using a Bodie plot. But when I did a transient analysis, I was seeing 49 dB of gain. And I was seeing 65 dB gain at 1.5 megahertz, and here I'm seeing 45. So it's a huge difference. So, but bottom line, I'm seeing 16 dB roll off across the bands here with the BitX 20 amp. So if you look at the newer BitX 40 amp, same 2219 IRF 510, but he introduces a 849 transistor here as a preamp, a preamp or a pre-driver, or whatever you want to call it. And if you look at the plot of that, I'm not even going to talk about the Bodie plot because it's garbage. I'm just going to talk about the transient analysis I did, and the gain I saw here. And you see, I'm getting a 5 dB roll off. So the BitX 40 amp looks as if it performs better across the bands, just as is. And I I'm not substituting any parts. I'm not changing the transformers. Now, part of the reason that the BitX20 may not be performing well is because of this output transformer here on the IRF 510. Because if you look at the impedance, the inductance, it's quite low. And you look at the inductance here at the BitX40, it's much higher. So this that may explain why the BitX40 performs better at higher frequencies. Okay, so then I looked at the micro BitX, which it's he's using push-pull configuration as well as he's doing parallel transistors. So he's using a push-pull IRF 510 configuration, and he's using a push-pull driver, but he's using parallel 3904s just to allow him to have more gain and less heat dissipation in these 3904s. Because I think that's why they use the 2219 transistor here, because it's got a higher, it could put out a lot higher wattage. So by him paralleling this and doing a push-pull, he could potentially drop the power output, the power dissipation from these transistors quite a bit and get a lot more power being pushed through. Same thing with the pre-driver. He's got 3904s paralleled. And if you look at his transformers, they're all 10 trifilar turns. And, you know, it's all 36 microhenries inductance, right? So, and if we look at this, we see that we get only 8 dB roll-off here. And the micro BitX power amp is supposed to be a multi-band power amp. So that looks really good. So then I went and I looked at this because I had this kit, this WA2EBY kit. He did a power amp. He is for QST or QEX. He won a contest for a power amp. It got published, and Far Circuits published a kit, a board for it, and it became very popular. So I decided to take a look at this. Now, this is just an amp. It needs about a 1 watt drive. There's no preamp here. So I thought, let me take a look and see how this amp performs. And so with, you know, about a 1 watt drive, this thing is pretty solid right across the bands. Like down here in 30 meters, you know, 30 meters and 20 meters, it dips down a little bit, but it's pretty solid. It's into 40s right across, 40 dB gain, but a 5 dB variation. So that amp looks pretty darn good. So then I took a look at the Hans Summers amp, which is a push-pull. He's got same push-pull, and he uses 2 BS170s to drive that. And Ken, I was asking Ken a comment because I ran into all kinds of problems with this modeling this amplifier. And Ken mentioned that this is basically a duplicate of the Tony Parks amplifier he had for, was it the not the hard rock, what's the soft rock?
Yeah, soft rock.
Yeah, so it was basically the soft rock. So he had a very, very similar amp. So I think Hans Summers lifted that from Tony Parks. Tony Parks probably lifted it from someone else. The only thing that I saw was that there was some discussion about putting a 75 ohm termination resistor here at the front to improve it. I tried it without this. I tried every which way. I could not get this amp to work well. I was getting a 16 dB roll off, 20 dB gain, and it just, the amp would not work well. And if you look at, you go to Hans Summers' documentation, he had people do independent testing of this amp, connect it up to like spectrum analyzers, and they were getting, you know, like a variation of a few dB across the bands. They weren't seeing 16 dB roll off. and they were seeing upwards of 24, 25 dB of gain. So something's wrong with this. And the only thing I could think of, there was this one circuit he had in his model, which was basically a temperature compensating circuit. So this line here was feeding the gain here for the to feed the, not the gain, the bias, sorry, was feeding the bias to bias these BS 170s. I just from my model, I just fed it in. I didn't want to model that because in his model, I can't remember which ones of these MOSFETs is actually attached to the BS 170s. So when it heats up, this thing puts out less bias and it pulls back the gain. So it's like a temperature compensating circuit. So that's the only thing, the only difference, but I couldn't do it. I wasn't going to troubleshoot it. And I said, you know what, just shoot the rabbit at this point. I'm not going down that rabbit hole of trying to figure out why that amp isn't working.
Can I say something quickly here?
Sure.
Yeah. Back when I started back in the hobby, I started with one of Tony's kits, and I found out that if you bought the BS 170 from a supplier or even China, that those BS 170s, they had to match almost perfectly. If they didn't match, it didn't work correctly.
Yeah, but
So,
this is simulation, Ken, where
okay, yeah.
where these BS 170s, they're identical.
Yeah. No, I just wanted to throw that in there just in case, if you came across building one and it wasn't working correctly. That's what the reason would be.
I'm not going to bother even. I actually bought one. I have a kit. When I was at Dayton in I think 2019, I think I bought one of his kits and it's sitting here. And so maybe I should build it, test it. But so this is my analysis. What I found, and I've just got a couple more slides and I'm done. So so I'm seeing significant roll off here. The micro BitX was a little bit better. The BitX 20 was terrible. Now, is it because of that transformer? Is it because of MOSFET capacitance? Is it something else? Independent testing of the Hans Summers amp, was good. I couldn't get it to work, so I'm just going to throw it out. I'm not even going to bother. I said, you know what, the Hans Summers, I'm not even going to bother looking at that any further. But definitely the WA2EBY, the BitX 40, and the Micro BitX, they seem to have much flatter response. With the WA2EBY, that's definitely a good amplifier, but it needs 1 watt drive. And so you need to put like a preamp, some kind of preamp there, which by adding that may limit the bandwidth of the amp. So that's definitely something for me to take a look at and play around with. And I think someone recently posted a message on the forum asking about where to get parts or boards or something for that WA2EBY amplifier.
What do you call it? Filters.
Yeah, I couldn't remember, filters or amps or something. But so, I'm not going to boil. So when I looked at those amplifiers, I said, I'm not going to boil the ocean. I am going to take those MOSFETs, the IRF510 and those other MOSFETs, which looked pretty good. I'm just going to drop them in as is. I'm not going to go and tune transformers or tune things. I'm just going to plug it in and see if it works better. I'm not going to boil the ocean here trying to design a better amp. I'm just basically wanted to see if a different MOSFET in these amplifiers would perform better. So what I needed, this is what I need to go and do in order to do that. I would have to select the MOSFET bias, right? So I'd have to set a bias. Then I'd have to figure out the input drive level. Then I'd have to measure the purity coming out, because I'd have to make sure I'm 44 dB. My harmonics are at least 44 dB below the carrier, below the fundamental frequency I'm putting out. I need to measure output power. I need to also look at the power being dissipated by these devices, because sure, I could drive the crap out of them. LT Spice will say, you're putting out 100 watts, but the device is putting out 200 watts and it's going to melt down, right? You're going to have the China syndrome. And you got to also measure input, output, impedance. So there's a lot of things to measure. And if I was to do this manually, running a simulation, going and measuring waveforms would take me forever. So I have to figure out how to do automated measurements. And that'll be another talk where I'll talk about how to do automated measurements in LT Spice. Then I had to figure out how to do FFTs in LT Spice. I thought I could, but man, did I not know how to do it. So basically my strategy was there's a whole bunch of things I had to measure and control. And what I would do is I would adjust some of these things. I'd only measure these things. The purity. So I'd measure what the signal coming out is, what the harmonics coming out is. I'd measure the output power. I'd measure the power dissipation. So I would select optimum. So I'd adjust these parameters, stick in a MOSFET, adjust the parameters, and select the best purity, the best output power, and the lowest power dissipation. And of course, I'd have to factor in the low pass filter. And my final slide here is just a word about low pass filter. So if I look at a little bit of math, we needed 44 dB down. So, and if you look at the power of the harmonic versus the power of the fundamental, or the voltage of the harmonic versus the voltage of the fundamental, I could work out the ratio just by doing some math to find out the voltage of the harmonic must be at most 0.63% of the fundamental. So whatever voltage the fundamental is, I have to be at below 0.63% of it, right? So, so that's what I wanted to go and do without looking at the power amp, because if you look at here is the harmonics. So this is the dB below the fundamental that you get from a typical power amp. Here's the second harmonic, third harmonic, fourth harmonic for 80 meters, 40 meters, 20 meters. And if you look at, and this is, if I slot in a low pass filter now to that power amp and I measure the harmonics, this is what I'm seeing. So here, if I look at the second harmonic for 20 meters, the filter is knocking it down 49 dB. So, that in itself, it's knocking it down 49 dB, which is well beyond the 44. So I could be almost at plus 5 dB above the carrier, and I'd still be within legal limits. So my rule was, I'd said, okay, I would select an output of the power amp that the harmonics has to be well below 0 dBc. So in summary, going forward, that's what I kind of would do, is that I would assume all components are okay, only adjust the biases and the gains. I would just plug in different MOSFETs. I would measure the spectral purity, measure the harmonics, measure the output power, measure the power dissipation, forget about the low pass filter. So I just picked some value below 0 dBc, some arbitrary value, and I'd work towards that. And I would select the best amp. So in my next talk, I'll talk about how to do an FFT in LT Spice. And then in a subsequent talk, I'll talk about making automated measurements and how I was able to quickly go and analyze these amps. So that's it.
Okay, cool. Very good, Dave. Questions, comments from anybody? Okay, let me see who's got their hands up. Peter.
Very good, Dave. I've been thinking an awful lot about that D612. It's one of those projects that's been sitting in the drawer for a long, long time, and I don't want it to defeat me. So I'm glad you got the interest back in this again. One thing I did notice, we talked a long, long time ago about it, was a push-pull configuration on that would solve a lot of the harmonic problems that we were seeing with the original PA. But I understand your philosophy there by taking another bunch of MOSFETs and drop them in there, and hopefully you find something that will work better. And if it does, then that's great. Then there's not a great big huge redesign, because anything other than that, it will be another redesign. One thing, a comment about the heat, you touched on it a bit there. Of course, I know I was generating an awful lot of heat with the driver circuit, probably maybe even more so than the PA itself, the final, I mean. But what was my other comment? I forgot what my other comment was on that one, Dave. But anyway, do you think I don't know if you've already done the testing or not, but I'm wondering if by just dropping in different MOSFETs, and if the different MOSFETs are the internal characteristics, the capacitance I'm talking about now will be different, and would you not maybe have to take that into account with the associated circuits feeding that MOSFET?
Of course. You have to, because you're changing components, and but these amplifiers, I think people just throw stuff against the wall and they say, okay, I'm just going to put this in. You know what? There's so many variations and so many different, transformers and all kinds of stuff with that IRF 510. I don't think there's any math involved. I think there was one core design and people start tweaking it. So you're right, Peter, but my assumption was I just wanted to see if I could drop in a new MOSFET and it would make a difference, and it does. It does. Trust me, it makes a huge difference.
Okay, well, that's good news. Because it
does, and you'll, if you go, because I do a lot of searching, and you'll see people doing that RD 16HHF MOSFET, whatever it is. A lot of people are using that instead of the IRF 510, and that's why, because it's got the internal capacitance is a lot bigger.
Okay.
Right? Or
Okay.
smaller. If it's smaller,
much smaller.
It's much smaller. Sorry, much smaller. Duh.
Okay, go ahead, Hassan.
All right, can you hear me?
Yep.
Dave, since you're doing simulation, I was wondering if you used an op amp and took the feedback signal from the output of the MOSFETs, and could you get a perfect response that way?
Oh, and feed it back to the op amp?
Yeah.
Hey, that's not a bad idea. That's not a bad, because if you could just take that, you'd have to, do some kind of voltage divider to bring it down. Right. But yeah, you could use that, and and that could be like a AGC, right?
Well, essentially, then what happens is your whatever transistor you use, it becomes an ideal transistor, because the op amp basically adjusts and compensates for whatever it is.
Yeah, that's actually, and then you could add some kind of a feedback, like a pot or something to control how much signal you're feeding back, and that can adjust
variable gain. Yeah, variable gain. The thing is, if you do it in Spice and use an ideal op amp, it should work. But I'd be curious, if you use a regular op amp, how fast does it have to be? What are the limitations there that cause it to deviate?
Yeah, that, you know what, Hassan, that is a very, very good idea to drive, because mostly op amps, the feedback network is looking at the output from the op amp, feeding it back. But if you feed it back downstream, no, that's actually and you know what? It would be better if you took it from the gate of the MOSFET, because that's what gets attenuated.
Interesting. I never thought of that. but
Yeah, because you want the gate voltage to go up to get that MOSFET to perform better, right?
true, but if you take it from the output, you go with everything. It's all.
Yeah, true. Yeah, I know. But hey, you got the wheels going.
I'd love to see what you come up with, because that's a. I've got a cheap DC power supply from China which uses this trick, an op amp with a pass transistor, and it works perfectly. But I've always wondered if it works at RF. And
Yeah, that's actually not a bad idea.
That'd be like having ALC on there.
Yeah, well, is it AGC or ALC? I guess it's ALC, automatic level, right?
Yeah.
Same thing, probably. Well, I guess slight difference.
Depends on what person's definition it is.
Yeah.
Come up with a new definition. It's yours.
And
DLC, Dave limiting
Yeah.
circuit.
and Peter, that's how you can adjust the output power too, as well, by adjusting the feedback, because the op amp will ramp up the gain, ramp up the power, the voltage going to the next stage, right? And you get more amplification going out. So you just feed back more or less of the signal, so it tries to bring the signal up more to match it, right? That's interesting. Very, very interesting.
Okay. Anybody else with a question or a comment? No? Good. Very good, Dave. That was interesting. Next up is Peter with LT Spice Tips. Take it away.
Okay, just a short. Can you see that?
Yep.
Oops. Oh, darn. Sorry about that.
It was working.
I know I hit the wrong button. There we are. You can see that?
See your picture.
What do you mean my picture?
You.
Oh.
No, I could see your screen. It's working.
Oh, there we go.
Okay. Just a short little topic here on the Monte Carlo analysis. Okay, what is it? It's an analysis method that's used by engineers to increase the reliability of their products. It basically analyzes the effects of tolerances or errors due to electronic components. And the pictures are just several little different ways of looking at the analysis. And why is it called the Monte Carlo simulation? Well, it was first invented by Newman and Ullm during World War II, of all places, to improve decision making under certain conditions. I wonder what those decisions they were trying to make. Anyway, the simulations are named after, of course, the popular gambling destination in Monaco. And we all know about chance and random with slot machines and dice. And I guess Eric is going to be doing a little bit of that next week. So the two circuits that I took a look at, the one on the bottom right we'll talk about first. Nothing fancy about that. We're all familiar with the different layouts of the components in there. The V2, V3 is that gives the positive and negative rail to the op amp. The sine wave directive is 0 DC offset, 0 offset, 2 volts, and 500 hertz for the frequency. What is different is up at R2 right here. And we have a statement here, MC for Monte Carlo. The 200 is the nominal value of R2, and the 0.1 is 10% in this case. So if you went 0.2, you're talking 20%, or 0.05, you're looking at a 5% tolerance. Now, if you ran the simulation just like that, it wouldn't do much for you because you'd only get one sweep, and that would be the end of it. And of course, the whole idea is to see a multitude of sweeps. So you have to include a step parameter in here. and you just put in the letter R, and you're going to be running 1 to 5, so 5 simulations in 1 steps of 1. I did that just because I think in the next one it's a little bit more than just 5 runs. I think in reality, if you're doing something like this, you'd probably be more like in the neighborhood of 50 or 60 or 75. You would put in there just instead of the 5. But for the sake of this discussion, it's just a small number. The circuit up here in the top left is actually a circuit that's in that comes in the LT Spice in the I think they call it the education directory or something like that. And basically, it's the same thing, except well, here they've put in several of the Monte Carlo directives in all the capacitors and all the inductors. What they've added in here, a little bit different, is the parameter. Instead of putting the number in here of whatever tolerance you want, they've used a variable. So when you come over here, when you want to make changes with your tolerance, you just have to make one change here.